I got a question here in the break. If all of this was on the protocols or the actual encryption and not on the authentication, we will actually be covering a lot of authentication attacks in these slides on related attacks. So broken presentation, yes. Broken slide here again. We got a bunch of attacks which they're not attacks on the SSL TLS protocol. The protocol is not at fault here, but the infrastructure around it is a bit shaky.
And the humans.
Yeah, and the humans, yeah. The humans are part of the infrastructure.
Man-made problems.
So, MD5, you might have heard people saying that you're not supposed to use MD5. That's old. I hope someone has heard it. The MD5 pre-image attack basically works like this. If you have a trusted third party, which you send something to and they sign it, you tell them, please sign this. So this might be, for example, hello, I'm Peter, I want a certificate from you. And they take what you have provided and sign it. And what they're actually signing is not the message, but they're signing the MD5 of your message. The thing here is that it's complex but possible using flaws in MD5 to create two messages which will actually give the same hash. So you take here what they signed and give something completely different to the victim. Yeah, and here the direction of the arrow actually changed in the conversion. It was correct before, I promise. So, what software have you been using? Where are you? There? Yeah, we're using different PowerPoint things and everything breaks. But the thing here is that you can actually send, for example, a malware, and it will seem like it's signed by the trusted third party. You can actually create two certificates which have different plain text but the same hash. And you have to create this. You can't do this attack after you have created the message. You need to create this evil pair in beforehand. So you can't take any message and create a collision. You need to create sort of an evil twin pair with one good twin and one evil twin. And in 2008 we saw the coolest supercomputer ever. It was over 200 PlayStation 3 machines being networked together to break the internet. And they succeeded. They actually managed to create a certificate request where one what they provided was the good twin, and that basically say, hey, I want the normal certificate, and the certificate request was signed by the certificate authority, and little did the certificate authority know that there existed an evil twin which said hello, I want to create a new certificate authority. So, using the evil twin, they actually had fooled some SEA to create a new SEA. So suddenly there existed a new certificate authority, which was created by doing an evil clone. Luckily, this was done by a security researcher team. They didn't tell the CIA, the certificate authority beforehand that they were going to do this, because they figured that someone is going to say no if we ask nicely. So they just did it. and then they notified everyone that this is a rogue SEA certificate, and then they published their research into this topic. And for background, this attack happens in 2008, and I think it was in 1996 people started saying we need to move away from MD5. It will be broken.
A question. It's still interesting that one of the root certificate that you showed early on in the presentation had an MD5 sum as
Yeah.
a root certificate. So what prevents you from create a correct key that matches?
Yeah,
such
yeah,
certificate?
but this is a pre-image attack, meaning that you're creating putting a lot of computational research as well as scientist working hours into creating a pair where one message is saying one thing, one message is saying the other thing, but you can't take any message. You need to have two messages, and you need to have spare room. You need to have fields which you can't where garbage is accepted. So this is a pre-image attack because you have to when you're sending something to be signed, you have already put a lot of computing hours into enabling the attack. You cannot take an existing message and then creating a collision. So creating a collision later on is a much tougher crypto problem. So in Flame 2012 we saw what people are claiming is, depending on who you ask, it's the United States, and according to some it's the Israeli government. But people are basically claiming that this is a state-sponsored malware. And this was the first time we saw a malicious use of pre-image attacks. So what they actually did was that they asked Microsoft, we want the terminal server license. And they got the terminal server license. And what they had done was that they had an evil twin, which wasn't the terminal server license. The evil twin was a certificate valid for signing Windows updates. And there's fairly large differences between this message and this message, leading for scientists to conclude that this is not the same attack as we saw before. It's exploiting that MD5 is weak, it's doing a secondary pre-image, but there's completely different research being put into making these attacks. So the guys who made this attack, they were not copycatting the previous attack. They had really good computer scientists to make a new, different attack on MD5. So this was made by really good cryptanalyst guys, and that's also one of the reasons why it's very unlikely that this attack was carried out by a few random hackers, because they definitely had access to bright guys. And stolen keys. This is really the most basic attack. If you want to be someone else, you just steal their crypto keys. And what we have seen a couple of times is that vendor keys has been stolen for code signing. Let's say there's been a lot of hardware manufacturers, those who make drivers and such. Their keys has been stolen, and they have been used to push malicious software. So most of the attacks we have seen have been on code signing keys, but these attacks could of course also be used for SSL attacks. So Duku is another one of those malwares which people are claiming are the United States or someone similar. And they used we know that the theft must have occurred after 2009, and it contains keylogging software, and Simon McAfee claims that this was found at a lot of certificate authorities. So they actually pushed malware to the certificate authorities designed to steal information containing a stolen certificate. So it's a really interesting combination. And the famous Stuxnet, which people claims was used to disrupt the Iranian enrichment facilities. The Stuxnet actually used two different certificates, and they could actually track down on these signatures when the signature occurred. So we know the dates where they did funny things. And yet another related thing is attacking the actual certificate authority. You break into the certificate authority and you either steal the certificate authority's keys, if that's possible. Hopefully they're storing it into a hardware model where you can't steal the key, but you can issue certificates from them. And once you have gained control over a certificate authority, you can spoof almost anyone on the internet. So if we look at the first famous SEA breach, we had the Komodo incident, where some people claim it was state-sponsored by the Iranians, while at least one person claimed to be a single hacker being responsible for everything. And they actually went after a small reseller for Komodo, and they just managed to get a few certificates before the alarms went off and people managed to terminate this attack. So this guy wasn't able to do much evil. And then 2011 we saw very similar attack, also apparently Iranian origin, and Google Chrome sets off its alarms because Google Chrome is detecting man-in-the-middle attacks. If they find that Google is presenting the wrong certificates, they are alarming Google that, hello, I'm a Google Chrome and I'm witnessing a man-in-the-middle attack. So based on Google alerting the community that this SEA had been breached, there was a bit of different information. First it was just a few certificates stolen, then it was 531 certificates, and then people weren't really sure. And basically everyone revoked trust because there was various mismanagement involved in this incident. And after everyone had revoked their trust, there was this SEA filed for bankruptcy. And we have got the good, the bad, and the really ugly. So let's say if we have a certificate authority, they're supposed to protect the internet. What if they are just doing really stupid things? So we have DigiCert Malaysia, And DigiCert Malaysia is not the famous DigiCert. They are a completely different company. Which not all customers of our company realize, because some people actually removed all DigiCert keys. So some of our consultants were very angry, thought we were doing something wrong because our encrypted webmail had a bad certificate, some people thought. But it was just a CLAT thing. They actually published certificates which were really, really short. They were so short that you can crack them on an ordinary PC. So people actually cracked this to distribute sign malware. I think that was how it was found. And there was a bunch of problems with the certificate as well. And then we had the Turk Trust, which they issued certificates to the Turkish government, and the Turkish government had these bad certificates for at least a year without anything strange happening. And then on Christmas, Google Chrome engineers had to cancel their Christmas because Google security was alerting that we are having a man-in-the-middle attack. You need to cancel your Christmas. And so in the very first days, people thought that the Iranian government, the Turkish government, had issued a man-in-the-middle attack. But as details emerged, it seemed to be much stranger. Turk Trust barely can speak English, so it was very hard to actually, when they responded, it was actually very hard to even understand the English. But what people found out eventually was that they had done 2 bad certificates, just 2. And they had given it to 2 different Turkish governments. The first Turkish government thought, no, this is wrong. And they connected back and said, you gave us an unusable certificate. And they looked at what was the certificate, and it was basically a new certificate authority they had given away. And then you might think that they audited and checked if they had done this problem before, but instead they just, alright, we revoke this certificate. And it turns out they had given another Turkish government a bad certificate. And suddenly one day, right before Christmas, a network engineer thought that it was a good idea to take this certificate and install it into his firewall. And suddenly he accidentally enabled a man-in-the-middle attack against the employees of this Turkish government. And some of the users there were using Chrome. So from what we can gather, this was probably no malicious intent here at all. They were just quite bad at doing the certificate authority job. But these guys, they're still in business because we decided, or the world decided that these people, yeah, that was just accidentally stupid one time. We'll give them a new chance. Yeah.
Okay. Anybody still awake? Running out of time. I have this about Snowden and trust post Snowden. We want to hear this, or should we go more into coding and validation and what you actually should be doing? Want to hear this, or?
Yeah.
Okay, do this the fast way. If you look at what Snowden relations so far has shown us is one thing, and that is actually that open algorithms, as we know it, is actually pretty good. It seems that NSA and friends don't have magic bullets that can break through AES and attack RSA ciphers, for example, very, very much faster than what we can do in the open world. So communication security, if it used properly, actually seems to work. The math seems to work. And if you look at what NSA is trying to do, is that they're trying to find and create easier methods to gain access instead. So if they can't attack the math, which is I'm expecting them to do, that's what they're supposed to do. That's their job, to break encryption and listen on traffic. But what they are doing is that they're looking at attacking implementations, and they're actually trying to force, both looking for weaknesses in implementations, but also influence and strong arm implementations into introducing weaknesses. The last things we're talking about, hearing about this, is IBM and Cisco, for example, getting strong armed to deliver equipment with backdoors in systems sold to different countries. And if you heard all about discussions about Huawei, the big Chinese vendor, telecom vendor, that's what they've been accused of so much that they actually tried to decided for a while at least to pull back from the US market. And now NSA is doing the same thing with Cisco and IBM. So that's pretty bad. And also what seems to be happening is that NSA targets standard development to change the standards being developed to be weaker than we assume them to be. And NIST, for example, is one of those guys that clearly has been targeted. ISO ETSI SAGE. SAGE is the security group for the mobile telecommunication organization, ETSI. In my opinion, they have a terrible record. They have standardized ciphers and algorithms for GSM and 3G, 4G, and every one of them is really, really bad. They've even taken good algorithms and changed them to become better, and it turned out to be really bad. I really have no trust in SAGE, actually. And IETF, who standardizes SSL/TLS, seems to be, the discussion is, have they been trying to influence development on that one? And also, of course, attacking data at rest in use. So cloud services, Google, Apple, Microsoft, for example. So they try to walk around. If they can't attack the algorithms and the communication, they try to go for the endpoints and go for the implementations and weaken those guys to get it better, easier. And in my opinion, I expect NSA, FRA, and everybody doing this, attacking algorithms. I expect them to actually listen. I expect them to look for weaknesses. But what they're doing here is to actually weaken the civilian systems to make them worse. That's what I'm having a big problem with, in my opinion. So what is suspect then? If you look at this, and as I said, openness seems to be what protects us. And I talked about random generators before, and Intel has this fantastic random generator called Bull Mountain in Ivy Bridge and Haswell processors. I've tested this one myself quite a lot. It's fantastic. It gives great randomness, random values, and huge of them. I can get gigabits per second easily. And I tested it, and it's very good quality. But how do we know that it is a true random generator? That it actually works the way Intel says it is? Or if it actually is one of those pseudo-random generators with a seed that NSA, for example, knows about, and just keeps generating values. But they can actually look at it and extract it. We don't know. So big discussions going on mail lists and with Intel to actually be able to get the design information about it. And also be able to get at least read access into the entropy sources, so we can read out and see what's actually being generated by the entropy generator. And we know that NSA actually has been attacking random generators. In 2007, Microsoft researchers looked at the NIST-specified pseudo-random generator called Dual ECDVG, and I suspect that this might be a problem because it seems to leak key information. If you take the seed value and put it in there and generate a lot of values, you can actually look at those values and recreate the seed value. And Snowden seems to confirm that yes, it was actually done in that one. And also, if you look at algorithms, NIST and NSA was involved in specifying DES, many years ago. Elliptic curves. NSA is one of the big patent owners on elliptic curve cryptography, together with Certicom. And they have actually been involved with NIST to specify those curves. So can we trust LDP curves or not? How do we know that they are correct? They say that the curves selected in special NIST curves and IEEE curves have been selected for good performance and good strength. But do we know? There are magic values in there. We don't know. And then protocols. On IETF mailing lists and cryptography mailing lists, there's big discussions going on with people that have been involved in the SSL TLS standardization groups, because there are known people from NSA there, and some of them are. One of the things that have been discussed is the session renegotiation that you can actually do. That you set up a session in SSL TLS, and one of the peers can decide, well, I want to have another cyber suite suddenly in the middle of it. And you can do a renegotiation. And that's one of the things that have been discussed. Is that really useful? And would that be actually possible to exploit them somehow? So there are, and as Peter says, it's an interesting time because a lot of these things are being reevaluated right now. And then, of course, high security modules used to generate keys and store keys and operations. And then, of course, closed source libraries, frameworks, particularly proprietary solutions. So companies like Microsoft and Cisco, IBM, is all seem to be losing trust quite a lot right now. As I said, random generators, weak keys, no real random numbers, algorithms, weak algorithms, not expected strength, protocols, key leakage, session hijacking, and of course implementation, backdoors, and unauthorized access. I'm just going to. So what is being done then to solve this? As I said, there's a push to try to force or make Intel, hopefully, to open up a little bit more about Bull Mountains. And one thing is interesting is that just before Snowden revelation started, there was a big discussion in the Linux community to, if you're using an x86 processor with Ivy Bridge or Haswell or having the Bull Mountain random generator, it will actually bypass the whole chain I showed you earlier. So the whole thing with filtering and estimation and using the random generator or set random generator in dev-random would be replaced all the way through with actually what comes out if you read RD-RAM instruction in the processor, because it was considered to be so good, so you don't actually have to use that. And there was a guy that resigned from Linux community because he didn't agree that this was supposed to be doing like that. Instead, we should take the RD-RAM values coming out from the processor and put it in as an entropy source, and then use the whole chain as normally. And so the discussion is that should we actually use it, and should we use it as a replacement for the whole chain, or just use it as one of several entropy sources? There are a discussion going on, and I'm going to Stockholm next week to actually start looking at if we can sort of develop a open and transparent high security module. That is a random generator that sits on a card and implements crypto and implement PKI-SC CS11 protocols, so we can actually run accelerated support for SSL TLS on something that we really can trust. And we don't know how far down the rabbit hole we can go, because if we're going to go down to an ASIC, an FPGA, or how we're going to implement this in hardware, where do we put the limit on the trust? Can we trust the FPGA vendor? Can we trust the ASIC vendor, the chip fab, for example? Where do we actually put that limit? And where can we section it so we can say, we will put the entropy generator on the outside of the chip, so we can control that one, and we put the PRNG inside of it instead. And that's going to be interesting to see. And it seems to be going to be sponsored by IETF and ISOC. So very interesting. And as I said, new algorithms. There's a push to define new LDP curves to be standardized into, for example, SSL TLS, replace RC4 with other stream ciphers, and then move away from dependency on NIST. NIST has lost a huge amount of trust. And if you, I don't know how much you follow, but we have MD5, SH1, SHS2, and then for 6 years now, we have been developing a new set of hash functions that's going to be standardized by NIST called SHA-3 And the algorithm that won that was Kesak from Belgium, a very nice algorithm. And in the midst of all the Snowden revelations, NIST said, okay, we have selected Kesak, and here is our proposed implementation or definition of SHA-3 based on Kesak. And what they presented was something else that has less security than what actually won the competition. So they suddenly changed the rules, and at least the authors that had all the other competing algorithms, the finalists, for example, Blake, for example, because there was a huge importance during the competition in performance, because the problem with SHA-2 algorithms is that they're much slower than SHA-1. So having people move from MD5 to SHA-1 to SHA-2 is going to give you a huge performance hit. So that's why people are reluctant to use SHA-2 for a number of reasons. So NIST said we need to have something that is stronger, is based on other primitives, because SHA-2 is very nearly related algorithm-wise to SHA-1. We want to have something that's really different in the way it's in internal workings, and we need to have good performance. And Kesak is really different from SHA-2. It gives great performance, particularly in hardware, but also in software, and it's supposed to give good strength. But there were other algorithms that also gave really good performance with about the same strength. And suddenly NIST takes Kesak and then they changed the strength requirements of it. So while the author of the finalists said, what's happening? So I've been following the mail list. That's a big meltdown, basically. That's a huge, and they are retracting it now. So it's going to be a new draft coming out in a couple of weeks that probably goes back to the original Kesak implementation. So that's one of the things that's going to happen. So NIST has really lost a lot of trust, and people seem to move away from NIST towards, for example, IETF in standardized work. And then several efforts to audit, evaluate, and implementations of different kinds. One thing I like is, I know how many of you use TrueCrypt? Yeah. A good software, and you can download the source code. But how many of you download the source code and actually compiles TrueCrypt yourself? Anybody? No, no. It's because it's actually quite hard to compile it. I think it's a Windows Visual Studio project, for example, starting out. Not many people, not me at least. And there's actually one that's published a blog where it actually tries to compile it and compare it with you can download. But there is a fundraise to audit the whole of TrueCrypt, and so far they got $16K US a couple days ago. But really good effort. So what can you do? Well, as I said before, test you generate and test you generate keys. Use longer keys. Try to move away from RC4, move away towards AES in SSL. But as you said, well, try to use GCM, for example, as a cipher mode, so we don't have the problems with padding oracles. Don't ever, never use MD5. I have customers that still use MD5, but that's because they have legacy equipment that was designed in the 80s. If you have anybody, and if you yourself design a new system, protocol, whatever, and you write MD5 there, tell me I'm going to kick your ass. Because don't go there. So at least use SHA-1, but SHA-2 at least. And if it's just fast hash function that you want to have, there are much better alternatives than MD5 today. They're much faster. So if performance is a problem. And I move towards TLS 1.x something. So use open implementation libraries, test replication systems, and also consider where you store your private keys, for example. When you generate a certificate, you need to protect your private key. And this is normal security strategy, and you need to do this anyway. Because as we can, if we have time, I think we're running out of time, but so I can Mozilla will stop you from using certificates with 1024-bit keys somewhere in January next year. So in a few weeks' time, if you have a certificate that has been signed with a root certificate with 1024 bits, your server, your clients will not be able to connect to your server anymore. So you really need to start moving to 248-bit keys anyway. And if you're using SHA-1 in 2016, Microsoft will stop supporting SHA-1 for new certificates. So there is a movement towards better algorithms and longer keys anyway, and particularly just 124 bits keys. You need to move to that one from that one pretty soon.
How do you mean that? Are you saying we should move away from triple DES?
Well, triple DES is why not? If at least you use AES-128 instead of triple DES, you get better performance, you get better security. So,
but you say also move away from AES?
No, okay,
No,
to AES. No,
okay,
Yeah.
all right. I was misinterpreting.
Yeah, sorry. Yeah, DES is deprecated and triple DES should be deprecated pretty soon. Coding. How much time do we got?
I'm not sure.
2 minutes.
How much time do you need? This is important.
Yeah, this is important.
We can
Go fast.
10-15 minutes.
Yeah.
Okay, so the short story is, if you have to write specific code for SSL, you are probably doing it wrong. I have found specific code which does things to change the behavior of SSL many times when I've been doing code audits, and every time, or at least almost every time, the coding which has been put in to change something about the behavior of HTTPS has been really wrong. So unless you absolutely understand what you're doing, if you're writing very new code for doing something with HTTPS, there's a big chance that you're messing it up. And one of the reasons why it's getting bad is because it's a complex protocol and it's a complex authentication thing which occurs. And whenever you're getting problems here, you're getting really bad error messages. If you're getting the error messages when you're developing code which using SSL, when something isn't working, you're getting an error message which often is completely crap. It doesn't really tell you what you as a developer should do to fix the problem, and then you Google and you copy the code which is the top result on Google, and is that the code you should be using in your production code? And it's no. So for example, if you are messing with the authentication checks, there are about 14 rules which you should do. If you're doing almost any of these rules wrong, you will enable someone to perform man-in-the-middle attacks against you. So if you're changing the rules related to authentication, you're almost certainly breaking the SSL TLS security. And you find this all the time. So unless you really know what you're doing, you're much better off hoping that the standard implementation is secure, because random changes here will break things. And when I've been talking to developers which have these sort of problems, I recommend them to move slowly and read the error message, because I know that it's painful. I said to one developer that we can solve your problem with just some debugging. It will just take a few minutes. It ended up taking some 4 hours to solve the problem, but it's logical. It's like every other technical problem. If you just look at it very carefully, you will find out why things aren't working. So this is what's wrong in most. These are the most common errors which I see all the time. And there's a big chance, if anyone of you are coding, it's a big chance that if you go home and look at the code which you or your colleagues have written, it's a fairly good percentage chance here that at least some of your code has these kind of problems. So one of the typical problems is you connect to a server. The server truthfully says, "Hey, I'm the Russian malware guy." And you say, "Okay, I thought I was going to talk to Google, but if you say you're Russian malware guy, I'll talk to you. I'll run whatever you provide." So this is the flaw. This you find in a lot of code. Yeah, we put the hostname verifier here, and yeah, we return true. This is the solution to a lot. If you Google for "I got an SSL problem and this is the error message," you will find almost the entire first search result will be filled with developer blogs telling you to write this code. And it kills security. There's no point in having SSL after you have put this code into your system. This is not just coding blogs. You find this in real production systems fairly often. So this really occurs a lot. All right. They're slightly out of order here, our slides.
No, I think it's still sort of jumping in here with the same thing, basically, or sort of. And the one big problem with this is that when we're writing applications, we use a security stack, or a stack that sort of hides the SSL TLS implementation for us, which is good because again, it's if you look at the OpenSSL, it's a real pain to use. But then you sort of have to trust the chain up here. So application, if we have a networking stack and we open SSL, and then we're using curl, for example, to do for an application to actually get something, and then you sort of have to, or it might be a wrap around that one. Things might change on the way through the stack. You have to sort of trust the stack. There is a paper that's just saying that why SSL is really bad. This is if you want to do a set up an SSL connection in OpenSSL. I don't know if you've done this. But this is the amount of course you need to do just to set up the context, and then all the course you need to do to sort of just to verify that it's actually correct or not. There's a lot of course, a lot of things set up in the context. And there's a paper here. This is, if there's one thing that you should look up and read, it's a paper by David Boney and his colleagues at Stanford University. A paper came out about a year ago. It's called the most dangerous code in the world, SSL something. It's really bad. They looked at applications. They looked at libraries like OpenSSL. They looked at curl and web carts and libraries in Apache, for example, and then try to see if they can force them. What happens if we set up in a middle stack? And will you get a connection, like you said, if you're talking to malware.russia? And basically everything, including in PayPal, webcarts says, yeah, sure, no problem. Here is your banking account information, no problem. And the reason why, and here's an example why that happens. This is curl. How many of you use curl? Yeah, curl is fantastic, but the interface could be better. And this is example. This is how Amazon suggested if you're writing code for using their FBS service in PHP, you're supposed to do this. They suggest these two lines. And what's in curl, you need to set two variables enabled to validate a certificate. You have the verify peer variable that is a boolean. If you set it to true, it will enable possibility to actually do validation. But if you then you need to set the verified host, and that one is an integer. And if you set that one to to 1, it's only going to look in the certificate if there's common name field. If you set it to 2, it's going to verify the certificate and do validation of it. But if you look at the code here, it actually says that one to true, and that one is evaluated to 1, which means that it's going to look at the common name, and then we're done. And this is example code from Amazon. The author of curl has been a lot of discussions about. He thinks there's been changes to the API, but still it's a problem. This is actually PayPal's version of this bug. They actually set the verify host to 2, but then they say this one to false, which means that validation is turned off completely. So that's when you're going to talk to PayPal. Another error in this is Apache libcloud. If you're going to try and verify your common name, and they have a function that you can call a verify hostname in Python, and it sets up a regex compiler for you, and you can feed it, and then it will provide you a true/false if it's correct or not. The problem is that it actually puts in a prefix or wildcard, so anything that ends in Google will actually verify to Google. So Moogle and Scroogle will be, and if you want to have malware, please go to Scroogle. So here's
Right?
Yeah.
So one of the problems which cause these kind of problems is that we're having a test environment in our development, and we want to be able to do SSL there. We get errors in the test environment, and then we create code to handle the problems in the test environment. So we're introducing code into test, which might end up in production for a problem which only exists in the test environments. And then I would suggest don't write code to handle these cases. You can start up, for example in Java, you can start up Java using a different trust store, where you can add whatever you need to run the tests. So instead of modifying your code, just modify the Java environment where you're starting, so that it trusts the test certificates. Don't mess with the code. Run with secure standards in test. If you need to test SSL in your test environments, actually use real SSL, so you don't have to make weird special cases for test.
I know we're short of time, but can I ask a question there?
Yeah.
So if you're developing against a mobile platform which is pretty locked normally, is there a good way of doing it in that case, where you can't just start up Java with a known trust source, or can you?
We have managed to do security testing against mobile devices. So in those cases we managed to get our malicious test certificates into the phone. So
Okay.
it's doable.
It would be very interesting to see how you do that.
I think Matthias has maybe most
Beer
recent.
later on.
Yeah,
I got
we'll
one
drink a
on
lot
the
of beer and then we'll remember. But yeah, you can do it in the Android simulator, and you can do it in on actual phones as well. But it's a little bit different how complex it is depending on which phone operating system. So this is really. This isn't really post-Snowden, I wouldn't say, because Google started this long before the Snowden revelations, but they introduced certificate pinning, where they require a higher standard of security than you typically get from an SSL stack. And basically, all Chrome browsers, they know the public key of Google. So even if the Swedish government or the United States government or whichever has control over a malicious certificate authority, if they force the creation of a certificate, it can still not be used to spoof Google, because Google Chrome will detect this. They know this is the key it should be. If it ever is a different key, we know we are under attack. And you can actually do this code I'm not saying that you need to do this for an average application, but you can actually do this if you want to do security coding, and then your clients can actually detect government compelled malicious attacks against you. This is a fairly complex thing, and it's from the OWASP pages. So if you actually want to do this, basically you're developing a high security applications which has higher security requirements than general SSL applications. The interesting thing here is that they're actually doing all the security which is normally done. So they're not just adding their own code, they're running the old code as well. So even if this new code they're introducing is broken, since we're running the old code, we are sure that it won't be less secure than the standard code. But that is a great idea. Whenever you feel that you need to write special code for SSL problems, ensure that you still run the old code as well, so that you're only adding special handling on top of the standard, not removing the standard code. And basically they're doing some horrible thing here to get the public key, and they're doing some string compares to ensure that you're actually running on the specific key which is hard coding into the application. So this is actually one of a few examples where it might be advisable to introduce new code into your application for handling HTTPS. You're adding security which is not normally there. And you can also request higher level of security than normally found. So remember we said that there's a lot of TLS versions supported. You can actually tell your system that I only want to run TLS 1.2, everything else I will reject. And then you can enable just the cipher suits you think are the most secure. Keep in mind, standard Java 7 will not support these suits. So if you go to the documentations, it's not supported, and you might need to install Bouncy Castle or some other third-party library to get the most secure versions.
Is this most applicable when it comes to situations where you have sort of control or relative control of both the client and the server? That is, you're pretty sure your users are sophisticated and use late version software, and you can set the configuration on the server yourself.
Almost all SSL TLS code I have ever seen is some client or some service somewhere needs to do a connection to an external system which is using HTTPS. So that's the most common case. You're making the client part and you're connecting to something. That is what developers typically have to handle or manage. And assuming you either know the configuration of the server and know it won't change, or you can agree with them. I mean, if you enable this crazy security and it's not supported, it won't work. And similarly, certificate pinning, you must have an agreement that with the provider, with the server, that they will never change their key.
Or if you are the server side as well. So for mobile development, this is actually really good practice, because then you control both the application and the rest.
Yeah, exactly. It's so there are a couple of examples. The Google Chrome is obvious. Google are making Google Chrome, and they are making the Google servers. So they know this server should never change. we should have control over the server. It should always be whatever we put there. So if they ever want to change their secret, their private key, they need to change all Google Chrome installations. And this is the same for, yeah, you make a server and you make a corresponding application. But I mean, you can do these kind of things where you're not doing certificate pinning. You can just agree on that we need to have a high security level. These protocols need to be supported. But yeah, if you implement a lot of security without having a promise that it will be supported, then it might break. Tar du? Eller?
Yeah, we talked about the problems and attacks and everything, but one thing that I think is really important, or we think is really important, is whatever you're gonna do, please enable HTTPS in your as more. Whatever you do with SSL TLS, it's not going to be worse than running an HTTP alone. So at least use HTTPS. And talking about longer keys, I said if you use longer keys or RSA, for example, in your certificates, so the performance is going to be affected. I'm going to show you the slides after this one. But keep alives are more important. But as we said earlier, keep alives can also enable you to be invulnerable. But you can also upgrade, for example, OpenSSL in your libraries to get the better performance. There's also an interoperability problem, as you said, with crazy levels of security. There was a blog post about a guy that enabled 8192-bit certificate, a key in his certificate, and none of his users could actually connect. It turns out that OS X and iOS by default supports maximum 496 bits in certificates. So you actually had to modify the clients to be able to connect to a site that has that. I don't know the state right now, but a couple of months ago, the maximum limit in Chrome and Android was on like 2,300 bits. And what's in the Explorer, I have no idea. But the performance, if you look at this Nginx running with 1024 bits key, and then 248, and then 4096, and you can see it's pretty rapid decrease in number of sessions that can be initialized against the server running. This is Andreas Jonsson at Roma that has done this benchmarking, and if you look at Light HBD, it falls off pretty rapidly performance-wise, and also Apache. But we can see that if we turn on Keep Alives, we get huge performance improvements. So that might be better to turn that on and then use longer keys. And then as I said, upgrading OpenSSL, for example, can provide you, if you're running on a pretty modern processor, can give you a huge increase in performance. This Xeon processor has the ASNY instruction set. It's an Ivy Bridge or Haswell processor. And AES really gives enormous performance boost on that performance if you upgrade OpenSSL to 1.0.1 at least. But even RC4 is actually getting a good performance boost by upgrading OpenSSL. I talked a bit just earlier that Microsoft is changing the way it's going to handle in the trust stores CA certificates for that using SHA-1 after 2.1.16. So that's quite a few years ago in the future, but still you should start planning at least for moving to SHA-2 in the next upgrade of your certificates. As I said earlier, also Mozilla has this deprecation of MD5 and keys with 1024 bits. It's been going on for several years, and this is the big one here right now, December 31, or soon after this date. They will disable the SSL encode signing trust bits for root certificates with key size smaller than 248 bits. This is a few weeks from now. So if your root certificate, whatever your certificate points to, has a key that is 1024 bits, you're going to have a problem in early next year. So it's time to look at upgrading your certificate. if you're going to support Mozilla, if your clients use that. And we talked about forward secrecy. To enable that one, you should look at upgrading your library. As I said earlier also, it has a performance cost, both in CPU time and communication, more communication. And what Peter says, we need to test. We can't just blindly trust the random generators. We cannot blindly trust that the code we're writing actually works. If somebody actually makes a mid attack of you, will you still connect to the server or not? There are ways to do that. I think Qualys has SSL Labs website. Has anybody used that one? Yeah, you should. If you have a server on the public internet that are running HTTPS, you should use this one at least once to try it out and see what you get for result. It will talk to your server and go through your certificate, all the cipher suites, if it performs renegotiation, if compression is turned on, and everything like that, and we're going to present a very good report. So this is romab.com. They worked quite hard at getting an overall rating of A on their certificate. They support forward secrecy, good cyber strength. If we look at, for example, mundal.se, they get a B rating. This is actually, mundal.se is probably the most secure website in Sweden. We've been running, together with is.se, we'll be doing a big survey that's going to be published in hopefully any day now. We looked at all the websites, all the servers that are connected to the public part of in the SE domain, and Mundal is the only site that has a 4096-bit key. So there's somebody in Mundal's community decided that we really need to have a 4096-bit key. So, there's some really cool ones. There's one that has something like oh, we don't think 1024 is good enough, so we have 1027. So it's there's some really weird ones. But Mundal is getting a B rating. And here's one of my favorites also, A-banan. This is actually arlandabanan.se. They bought their certificate from a company in Dalarna, well-known CA, and it's really. It started out because when I was testing my code, I got an exception in my code that I needed to handle. I wrote bad code myself because A-banan.se doesn't have a common name in the certificate. So I need to handle that one. So I fixed the bug, and I started looking at the certificate, and everything is wrong. They have an alternative name that is wrong. They use really weird cipher suites, and they support SLV2, which nobody should be using, and it's a crap. And this is all on the bottom. So. And if you try to look at Omega Point, you get this. Nothing, because you don't use HTTPS. Another thing to look at, getting a couple of slides in the end here. I said that it's a client that sends doing the client hello phase. This is Wireshark looking at handshake from an Android device, and it's doing the client hello here, and we can see it says TLS 1.0, and it sends its cipher suite list here. And there's a guy in Germany a couple of months ago that realized that when he was connecting with the Android device and looking at it, he started to see, well, it's using RSA with RC4 MD5. And Android used to use AES-256 with SHA-1. And suddenly here, somewhere in between, Android switched to using these ones as the first in the preferred list. And you find out that Android has sort of, or Google has sort of outsourced the selection of cipher suites to Oracle, because this is from Java in Java 6. That's where the suite order is selected, and actually the suite order that is in Java 6 nowadays is what's in RFC 3227 or something like that, where SLTLS was first defined. So they've gone back to the beginnings, and there's many RFCs before that. I don't know what it looks like in Android 4.4 though, but this is if you think that RC4 MD5 is not good enough for you, you should change the order in your application if you're writing Android applications. There is also a good web page to do client validation. You can go to SL Labs SL Test My Client and with your browser or your client, and you actually talk to it and see. Yeah. So you get all this. And there's also one I want to point out is TLS Pretense. This is a stress testing tool, fuzzing, or if you like, or closed it, that will stress test your client to try to do man-in-the-middle attacks of it. It will put in broken chains and null byte host names and stuff to see if you still fail open or not. So if you're developing a SL client communication code, you should. This is one you can look at and actually test to see if your connection will be secure when somebody tries to do man-in-the-middle attack on you or not. I think we stop there.
I agree.
Yeah. Thank you.
I am certain of two things. You're thirsty and you have a lot of questions for this.